No.
Very cool. Thank you, Peter. Hi, everybody. Welcome back to our next high energy seminar. Thanks for joining us. We have a nice crowd building up today. So for one thing I want to mention before I start, I know Peter just mentioned this a few minutes ago, but we have new people. We are looking for more people to join us and help run these seminars. It's a great opportunity, especially for early career scientists, to meet other scientists and also gain some visibility at the CFA. So make connections, decide what talks you want to listen to. Let us know if you're interested. So our first talk for the day is from one of our newer additions to the CFA, Dr. Hiromichi Okon. He finished his PhD in physics at Kyoto University this past March and has now come to the CFA as part of a 2-year Japan Society for the Promotion of Science Fellowship and is currently working as a postdoc with Dr. Randall Smith. So his research focuses on understanding the plasma evolution, explosion mechanisms, and particle acceleration mechanisms in supernova remnants using X-rays. And here he's going to be continuing his work on supernovas as supernova remnants. And he's also going to be constructing X-ray models towards future high energy resolution spectroscopy by combining numerical calculations and lab experiments. So today he'll be talking to us about plasma evolution and particle acceleration of supernova remnants based on his thesis. So Hiromichi, welcome to the CFA and please take it away.
So, and thank you so much for introducing. So, and I'm talking about the topic of the supernova remnants. So, and supernova remnant is a astrophysical object after supernova explosion. So, SNRS is a major energy component in the galaxy. So, play an important role for evolution of the galaxy and so producing diversity structures. So
I'm gonna pause for a second. Are you sharing your screen? Because I don't see it. I don't know if others are seeing it.
I don't see.
And
it was being shared and then it stopped. So
can you see my slide?
Yes.
Yeah, better.
Okay. So yeah. So now I'm talking about the supernova remnant. So SNR is a major energy component in the galaxy. So basically SNR is often have bright X-rays from thermal and non-thermal particles. So thermal particles are shocked heat in the shock wave, and non-thermal particles are accelerated in the shock wave, and constitute of significant of cosmic rays. So today's talk theme is how the released energy is injected in the into the interstellar space. So I talk about the thermal and non-thermal aspect of this topic. So first is thermal topic. So here is an X-ray spectrum of a supernova remnant. So the X-ray spectrum have many lines from various ions and Bremsstrassner continuums. So these components reflect on the plasma temperature, ionization degree of ions in the plasma. So X-ray spectroscopy is powerful tool to investigate the plasma property. So many observations of SNR establish the standard plasma evolution scenario. So in this scenario, plasma cross to neutral immediately after supernova explosion and collisionally ionizing until they reach to CRE state. So recently, observations of SNRs reveal the presence of the recombining, peculiar plasma, so-called over-ionized recombining plasmas. So this plasma is namely recombination dominant. So here is a spectrum of the RP-SNRS. So you can see the strong recombination lines and strong relative recombination continuum. So RPs has been discovered in the frozen SNRs interacting with the dense clouds. And the formation process has not been understood, but a key seems to be so energy dispersion of the plasma. So this is because the RPs are often found in so plasma experiment. So this is a cross view of so plasma reactor. So plasma so cooled by so outer so cold shell and become overionized. So sorry. So our first aim is so to qualify in the so physical organisms RP in SNRs. And so we performed so especially in spectroscopy and so compare the plasma temperatures and ionization degrees and so shock clouds. So and today so time is so limited, so I focus on the W44 case. So and this is a so previous works of W44. So W44 is one of the famous so recombining plasma RP-SNRS, one of the RP-SNRS. The left is an X-ray image of W44 override with radio contents, and left is left shows that CO futures as indicator of shock cloud interactions. So an X-ray image have a small and so fine so structures correspond to the CO future. So we divided those regions into small sub-regions, and so we performed spectral analysis. Okay, so move to discussion part. So W44 is known to be the most violently collided with the giant molecular clouds, and in these regions, so specially extended moderately broad CO emissions are detected in the radio band. So these emissions are considered to be from a disturbed and so shocked cloud by the shock waves. And now, so these clouds are evaporating in the hot plasmas. So left figure is a so special distribution of so KT override with so same bed so emissions. So the RPs in the same bed regions have lower so KTE. So and in addition to the plasma temperature, so the recombination time scale, so NET is also important parameters. So the left so below figure is so NET maps and override with the same bear. So we plot and the values of KTE and NET, and we marked so the points in the same bear regions. So now, so plasma temperature is so sorry, KTE is the plasma temperature after so rapid cooling, and NET describes how so plasma is close to the CI state. So this and so right figure shows that silicon so ion fraction and against as a function of so recombination time scale. So the NET becomes smaller, the ion become more stronger, so ionized. So and we so computed so the charge deviation from the CI state. So this result suggests the RP in the stable regions are more cooler and more strongly ionized. So we so concluded that rapid cooling by thermal conduction is responsible for the so over-ionizations. So so next is, so how about the formation process of RP in the other SNRs? So the left figure is a W44 case, and upper left is so IC443. So, and the result on IC443 is similar to that in so W44. So this suggests thermal conduction is a plausible formation process of RPs. So, and detection of charge exchange emissions and hydrodynamic accumulation would be so necessary for the detailed so cooling mechanisms. Okay, so and next move to so second topic, so non-thermal aspect of so particle accelerations. So this is an energy spectrum of particle acceleration. So and basically, so non-relativistic particles in the plasmas are accelerated in the shock wave and gains energy, and so finally reach to the so relativistic regime. So and non-relativistic and relativistic particles are explored by the synchrotron X-rays and JEV2 and TEV gamma rays. So however, so sub-relativistic particles have not explored by any means from now. So the information of such particles are important to consider the non-thermal energy and considering the so induction problem in so DST scenarios. So and we so focused on the so neutral ion kephalites as a new channel to probe subrelativistic particles. So and this is because so basically so so electron in atoms can be ionized easily. So when the projectile particle velocity is equal to that of it. For example, so and if we ion case, the binding energy is about 10 kb. So the right figure is so ionization cross section against the normalized energy. So and so for electron case, the cross section has a peak at about 10 kb. And for proton and ion case, the cross section have a peak at 12 MeV per nuclei. So and this and under this so strategy, so we searched neutral ion kephalites from Supernova Remnant interacting with molecular plots. So this is one example of so detection of the kephali. So this is also an Suzaku spectrum, and so we detected so significant and enhanced so FE kephalites. So and the gamma maps support our scenario. So and actually, so we detected so recently, so we detected so FE kephalites from so other SNRs. So next, so question is that the subrelativistic particles are so emitting that so ion kephalites are so proton or electrons. So the left panel shows that so stacked spectrum, and the spectrum has so neutral kephalites and non-thermal component. So non-thermal component would be so non-thermal Bremsstrahlung. So the one of the powerful tool to distinguish two cases is so the value of equivalent width of this FE kephali lines with respect to the so Bremsstrahlung. So right figure is an equivalent width against so particle so index of so subrelativist particles. So we estimated that so equivalent width with so stack data and equivalent width would be is so more than 0.6 kb. So this values requires a proton case. So and this result prefer so and our Suzak data prefer so proton case. So however, so this discussion so contains some ambiguity point because so the equivalent width depends on the so FE abundance and so on. So we need so more solid so means to distinguish so these cases. So we focus on the so multiple ionization process. So this is a if we care for spectrum and obtained by so ground experiment. So if projectile particle is a proton, so the observed spectrum has K alpha 1 and K alpha 2 peaks. So this is because single ionization occurs. So on the other hand, so projectile particle is oxygen. So the spectrum has a so complex structures. So if the particle is so oxygen, so if we atoms are more so multiply ionized, and so if we alpha lines so shift apart. So so inner so L shell so ionization make so large shift. So and the peaks structures are and resulting the so splitting the peak structures. And inner outer so M and N shell ionization make a small and line shift. So each peaks become broader. So we consider so the detection of these structures support our scenario and the evidence of the so heavy ions. So I will so briefly talk about the model construction. So at first, so the intensity of the peaks. So intensity of each peaks can be described as a binomial distribution with ionization probability per electrons, so PRX, and the number of L shell vacancies. So we so calculate the PRX with so the ground data. So next is so line center energy and line width. So so these are estimated with so stacked so data. So and so with so phenomenological models. So next, so we so checked if the model covers match the experimental data. So left is a chlorine K alpha and right is argon K alpha case. So black is so experimental data and the red curve shows our models. So we so roughly so success the model construction of K alpha Li structures, so brought by so multiple ionization effects. So to resolve these structures are so high resolution spectroscopy by microcalorimeter would be necessary. So I think so XRISM satellite is a good option from now. Okay, so we this slide shows that if we can have a model expected with a XRISM satellite, so we assume the cosmic recomposition near the solar system.
About
so
3
black
minutes left.
is okay. So black is the sum of CR compositions, and red and blue and proton are contribution of proton and oxygen and iron contribution. So composition. So you can see KF L1, L2, L3, and so on. So these structures are so multiple caused by multiple ionization. So we target our target. So finally, I will show you one study of the feasibility analysis. So and we observed we observed the W28 with XRISM satellite with deep observation. So black is an observed spectrum and red is a total background. So the total exposure is so long, so 3 megasec. So I think XRISM and or Athena is the next satellite would be detect these structures. Okay, so that's the summary. So that's all. Thank you so much.
All right. Thank you, Hiromichi. We are taking questions now. And we already have one in the comments from Federico about the map of the iron K alpha line from Suzaku. Have you cross-checked Chandra maps to probe whether subrelativistic electrons evolve into larger energy electrons, TeV, and emit synchrotron?
Yes, so sorry.
So have you cross-checked the Chandra maps of iron K alpha with Suzaku to probe whether subrelativistic electrons evolve into larger energy electrons at TeV and then emit synchrotron?
Yeah, so in other terms, the question was that the spectrum you showed, is it the total spectrum or is just the thermal part? Is there a synchrotron part, a non-thermal synchrotron part to this spectrum as well? Or that's the entire spectrum you see?
Yeah, so
mostly thermal.
So basically, our Suzaku data are consistent with JEV2 and TEV data, and Hess or Fermi.
Okay. So you see the Hess. Sorry, I missed the Hess part. Okay. Yeah. All right. So you can say that at least from that small region on the top left, there are certainly electrons evolving from the sub-relativistic to the fully relativistic. So there is an efficient acceleration in that region. So that will be a possible conclusion from this, right?
No. So we detected enhanced neutral ion K lines from the expected enhanced and average GRXE levels. So
this means so this means in the same region you have you have the subrelativistic which produce the iron line and also
subrelativistic particles are created by two processes. So first is in the process of accelerating, but next second process is energy. So high energy particles, very high energy particles are lost energy and they reach in subrelativistic particle band. So and we check distinguish two cases. So I think that high spatial resolution spectroscopy enable us to this study.
So there are no shock accelerated particles there.
Sorry, and
okay, I think we can discuss more detail later. Sorry.
Okay, I see.
We have one question from Randall, and then we should move on.
Excellent talk, Hiromichi. Thank you. The cases that you've shown here are all mature supernova remnants, yes? These are all 10,000 or more years old. So have you looked at any young supernova remnants to see if, because the Zhang et al. Hydrodynamic simulations showed that you might get adiabatic cooling in young remnants.
Yes, so I think so.
Okay,
Then
yes.
because so in this seminar, so I exclude this discussion because time is so limited.
Yeah.
So I think so. So major cooling driver is major cooling driver are so thermal conduction and so real fractions. I think.
Okay, I guess I missed this slide. Thank you.
All right, thank you, Hiromichi. We'll move on now to our next speaker, Ana Trindade Falcao. She is from Brazil and received her undergraduate degree in physics from the Universidade Federal de Minas Gerais in 2017. She moved to the US in 2018 to start her master's PhD program under the supervision of Dr. Stephen Kramer at the Catholic University of America. She received her master's in 2019 and will graduate from her PhD next spring. Since she started the program at the Catholic University of America, she has been working on AGN outflows and AGN feedback, which has led to 2 publications so far. Anna, are you ready to go?
Yes, thank you. I'm going to share my screen right now. Okay, can you guys see this here?
Yes.
Okay. So first, thank you for inviting me. Today, I want to talk about X-ray outflows and how we can use optical and infrared footprint lines to track these outflows. So I want to start with this plot here that is from a paper by Cormandy and Ho 2013, in which they present this bulge black hole relationship. So this here is one of the main reasons why we study AGN feedback in the form of outflows. Since this process is likely the reason for the relationship between these 2 individual entities. So before I start talking about my studies on X-ray outflows, I want to briefly discuss the results of my studies on optical outflows, since this is where our idea for X-ray outflows came from. So in this study here, we had a sample of 12 quasar 2s, and our goal was basically to quantify these outflows, their masses, mass outflow rates, and then their kinetic energy and kinetic luminosity, which is basically the rate at which this kinetic energy is being deposited into the galaxy. So these here are O3 subtracted images, and they are from a paper by Fisher et al. 2018, in which they analyze the same sample of quasars. And along with these images, they also obtained the spectra for all these targets. And these spectra were obtained using STIS, which is the Space Telescope Imagery Spectrograph, and were taken through a slit-like aperture, as we can see here. Oops. Here we can see some of their measurements for these targets, like the velocity of these outflows, and then the full width half maximum, and also the integrated fluxes for these O3 outflows. And using their results for these targets and combining them with a photoionization modeling analysis, we're able to quantify these outflows. So here, for instance, is one of the most important results, which is the kinetic luminosity profile for these targets. So here, the kinetic luminosity is given in log and in units of ergs per second. And the maximum kinetic luminosity among all the targets in our sample was 1.3 times 10 to the 42 ergs per second. So After we quantified the physical properties of these outflows, we are able to evaluate their role in AGN feedback. So there are models for efficient feedback like Hopkins and Elvis, for instance, that say that these outflows have to have their kinetic luminosity to bolometric luminosity ratio lying between 0.5% and 5% in order to be considered efficient. So these models are for AGN radiating close to their Eddington limit, by the way. So for our sample, this ratio ranges from 3.4 times 10 to the minus 6% to 4.9 times 10 to the minus 2%, which means that these O3 outflows are not an efficient form of AGN feedback in these targets. So after that, we calculated how much mass an outflow would have to have in order to produce a ratio of 0.5%, which is the lower limit for efficient feedback. So we did this calculation for the most luminous target in our sample, which is Markarian 34. And it turned out that it would need 10 times more mass in order to generate efficient feedback. So these values here in green are the required values for efficient feedback, and the numbers in red are our measured or calculated values. However, when we compare this required amount here to the maximum amount of O3 gas that this quasar could possibly have at that position, we found that this number here is greater than this required amount for efficient feedback. So another question that we asked ourselves was, why don't we see that? Why don't we see this amount of O3 gas in the netherline region of Markarian 34? So one possibility is that the gas doesn't remain in the state in which emits O3 for long. So if this gas is not confined by an external medium, let's say a lane of dust and gas in the host disk, it will rapidly thermally expand. And as this gas expands, the density drops and the ionization state of the gas increases to the point where it does not produce O3 gas anymore, but it becomes X-ray emission gas. So in this case here, the outflows that we observe could be dominated by this X-ray emitting gas. And these X-ray winds, they may be responsible for the dynamic effects we see, such as the acceleration and disturbance of this gas. So this here is the scenario that we explore next. So for my studies on X-ray outflows, we explore this possibility that the dynamic effects we see in these galaxies are due to X-ray winds. So we use two of the targets in our original sample, Markarian 34 and Markarian 477, as case studies, since they are the two brightest sources in our sample. And they're also the two nearest quasars with the best resolved narrow line regions. So here is a velocity profile for these two targets. So the points, they are the deprojected velocities from the STIS long slit spectrum analysis. And the purple points are just the points with the highest velocities. So the curves, they represent the velocity profile of the O3 being launched from different radii from the black hole. And they were calculated using the equation of motion that balances the effects of radiative acceleration and gravitational deacceleration. So we can see that for Markarian 477, if we launch this O3 gas from very close to the nucleus, in this case here from 10 parsecs, we are able to match the observed velocities. We are able to explain these O3 velocities that we see. But we don't see the same for Markarian 34. Even if the gas is launched from very close to the black hole, we cannot get to the observed velocities. We cannot explain these velocities that we see. So I want to show you another velocity profile. So this velocity profile here now considers that the gas starts as a low ionization gas close to the nucleus. Then as it expands, it becomes more and more ionized, which is consistent with the findings of previous studies of low ionization gas rotating into the bicone. So this increase in velocity that we see compared to this other plot here, this jump in velocity, happens because a low ionization gas absorbs the photon momentum much more efficiently than a high ionization gas. And as we can see here in this scenario, it's possible to match, it's possible to explain these observed O3 velocities. But there is still a problem here because we don't believe, and this is based on some previous studies, that the O3 gas survives as O3 gas after the solid part of the line here. So even in this scenario, we cannot explain these O3 points, points that we see at about 1.5 kiloparsecs from the nucleus at such high velocities. So we believe there's something else is happening here, and I'm going to tell you what we think is going on. So another finding from the Fisher et al. 2018 paper is that the influence of the AGN changes with increasing distance from the black hole. So in the most inner region, the emission lines, they present high velocity centroids and high full width half maximum, which is consistent with outflows. At greater distances, the gas is still being ionized by the AGN, but the emission lines, they present low velocity centroids with low full width half maximum, which is consistent with rotation of the host galaxy. And this happens because there is not enough momentum in the radiation coming from the black hole to generate these outflows. They also identified a third kinematic component in which the gas has low velocity centroids but high full width half maximum, which they refer to as disturbed gas. And we believe that this disturbance is due to the impact of that high ionization gas or X-ray winds that I mentioned a couple slides ago. So if this is true, we can assume that these high ionization winds, these X-ray winds, are depositing kinetic energy into this O3 disturbed gas, which suggests that they may possess similar kinetic energy densities. So based on this assumption, we can characterize the wind that might be creating this disturbance. So what we did is we calculated the kinetic energy density of the O3 disturbed gas. And by assuming that this kinetic energy density is the same for the high ionization wind, we were able to calculate a velocity profile for them. So here in purple, we have the predicted X-ray velocities. And the gray points, they are the O3 disturbed, the projected velocities. And the red points are the full width half maximum of the disturbed O3 gas. So the gray and red points, they are measured quantities. And the purple points are our predicted velocities for the X-ray winds. So what we can see here is that these predicted velocities for these X-ray winds, they are very high. And when we take into account the characteristics of this gas and the fact that X-ray gas has a much lower density than O3 gas that it is disturbing, this gas could not be radiatively accelerated to these velocities, even if it originated very close to the AGN. So a more plausible scenario is that the wind begins as a low ionization gas launched from very close to the black hole, subsequently expands over its trajectory and eventually evolve into an X-ray wind, as I mentioned before. So this here is the first evidence that we have for the presence of this high ionization outflows in this target. And this is also supported by the fact that the Chandra ACES image shows extended soft X-ray emission, which suggests the presence of high ionized gas in this quasar. Okay, but we still have to explain the presence of those high velocity O3 gas at about 1.2 kiloparsecs, as we can see here. So what we think is going on in this case here is that the O3 gas is being accelerated in situ via entrainment by the X-ray winds, which originated closer to the AGN. So in this scenario, the X-ray winds interact with small clouds or filaments of O3 gas and carry them along the narrow line region. So to confirm our theory, we constructed a velocity profile for entrainment for the O3 gas as a function of distance. And what I mean by that is that if there is entrainment, this is how a velocity profile for the O3 would look like. So what we can see here is that in order to achieve the velocities that we observe at about 1.2 kiloparsecs from the nucleus, the O3 gas would have to have been carried by an X-ray wind with a velocity of 1.5 times 10 to the 3 kilometers a second for 100 parsecs, which could be explained by an outflow that was launched close to the black hole as low ionization gas and expanded to a high ionization gas, as we can see in this plot here. And this here is the second evidence that we have for the presence of these X-ray winds. So we have two different phenomena that could be explained by this high ionization outflows. In this case here, in the entrainment scenario, the X-ray winds interact with the small clouds of O3 gas, effectively sweeping them up. On the other hand, in the disturbance scenario, the X-ray winds, they may be interacting with a dense spiral of gas, resulting in compression rather than acceleration. So also the velocities for the X-ray winds in both cases are in the same order of magnitude, which means that these X-ray winds are able to do both things, disturbance and entrainment. So this high ionization component appears to be dominating these outflows, which suggests that there is a large mass of X-ray emitting gas in the narrow line region of this quasar. So to estimate the amount of X-ray gas in the narrow line region of this quasar, Markarian 34, we used photoionization models to construct radial flux profiles for the X-ray gas and to predict its spatial distribution. So as you might know, the X-ray emission exists in the form of ionized gas, such neon 9, neon 10, 07, and 08. And here on the left, we have the predicted radial flux profile for the neon 9. And on the right here, we have a comparison between our models for the neon 9, again in black, and the results of the X-ray image made with Chandra in red. And these fluxes here, they were measured by Peter. So thank you, Peter, for that. And here there is a comparison between our spatially integrated flux. So of course we have to consider the arrow bars, but we can see how well these numbers agree with each other. And so based on these results, there appears to be enough X-ray emitting gas to produce the observed dynamic effects we see. But there is still a problem, because when we study the optical outflows, we are able to fully characterize them based on the data that we got from Hubble, the spectra and the O3 images. We cannot get the same degree of details from X-ray observations. And this is because of the resolution of the instruments, and also because the X-ray detections, they have a very low signal to noise when compared to the optical spectra. So it's very hard to get accurate kinematic information for the X-ray gas in these quasars, which means that the characterization of these X-ray outflows can be very tricky and hard to do. So I've been working on a new idea that can help us solve this problem, which is the concept of X-ray footprint lines. So here on the left is a Sti's long slit spectrum of NGC 1068, which is a Cipher galaxy. And what we can see is that we can see here lines like O3 and then iron 7, iron 10, iron 11, and iron 14. And we can see that these lines, they show different spatial distribution when compared to the O3, which means that these lines, the iron lines, likely track different emission components. So this other plot here shows the cloudy predictions for the fraction abundance of some ions that produce some of these lines, like iron 10 and iron 14, and some other optical and infrared lines as a function of the ionization parameter. So The dashed lines, they are the ionic abundances for the ions that produce these optical and infrared lines. And the solid lines are the ionic abundances for the ions that produce X-ray lines. So we can see here that some of these ions, they peak over the same range in ionization parameter as the ions that produce X-rays, which indicates that these lines will be formed in a gas that is also the source of X-ray emission lines. So this is important and can really help us because these footprint lines, they are optical and infrared lines, which means that they can be detected by optical and infrared telescope like Hubble or James Webb, for instance. And these telescopes, they have the resolution to give us accurate kinematic and spatially resolved measurements. So we can use this here to measure the kinematics and ultimately the dynamics of this extended X-ray gas. So for instance, this here is an image from a paper by Kramer et al. 2020, in which they studied the X-ray outflows in NGC 4151, which is also a Seyfert galaxy. So they analyzed the Chandra spectrum of the X-ray gas in this AGN. And as we can see, these images, they show extended X-ray emission. They also measured an average line velocity of minus 230 kilometers a second, which suggests a significant amount of outflow of this X-ray gas. They also found a total mass and mass outflow rates that are similar to those determined using O3, which implies that the X-ray gas is a major outflow component in this target here. So they determined a total mass of X-ray in the narrow-line region of NGC 4151 of 5.4 times 10 to the 5 solar masses, and a maximum outflow rate of 1.8 solar masses per year at about 150 parsecs from the nucleus. Also, the fact that it doesn't appear to be a drop in mass outflow rates for distances greater than 100 parsecs may indicate that the X-ray component has a greater effect on the host galaxy than the optical and UV gas, and that these X-ray winds, they might be a more efficient mechanism for AGN feedback. However, even though the use of Chandra high energy transmission grading imaging to characterize these X-ray outflows is an improvement compared to the ACES image data that we used in our studies to analyze the X-ray winds in Markarian 34, this is still not enough to fully characterize the extended X-ray emission, since it's almost impossible to directly measure a kinematic profile for these targets. And another thing that we have to consider is that this kind of analysis here that uses the HETG can only be done for few nearby targets. So what I've been doing is try to reproduce the findings of this paper by Kramer et al. 2020 on NGC 4151. And so in order to do that, we generated flux profiles from photoionization models for some X-ray lines that they detected in their study, as we can see here. And we also went a little bit beyond, and we predicted the flux profiles for some optical and infrared footprint lines. So here in these images, we have two sets of models. One considers that the gas is dust-free, and the other considers that there is dust within the gas. So we generated dusty models because in our studies on X-ray outflows, we proved that dust is needed in order to accelerate the gas to such high velocities. And also because previous studies such as Kramer et al. 2000 also indicated the presence of dust within the gas. So we use these flux profiles here to do the same kind of analysis that we did for the optical outflows. We use them to predict properties of these X-ray outflows. From there, we can compare our predicted quantities that we got using the footprint line analysis with the measured quantities that Kramer et al. Got using the Chandra HETG data. So just to show here is a comparison between our results for the mass in outflow in purple and the measured values from Kramer et al. 2020 for this target in orange. So what we can see is that first, these results, they agree very well. And we can see that this method works. And in this case here, we used iron 10 to predict the amount of X-ray gas in this galaxy. So our numbers are a combination between the footprint models for the iron 10 and the iron 10 flux measured with STIS, because we needed this to scale the iron 1003 ratio from STIS and the Hubble images to obtain these results here. So here are the numbers. We can see that our values are within the margin of error compared to their measured values. So we predicted a total mass of 7.8 times 10 to the 5 solar masses, while they measured a total mass of 5.4 times 10 to the 5 solar masses. And we're also able to confirm our predictions for the infrared lines based on previous ground-based studies. So just to make it clear, what you're looking at here is a comparison between the footprint analysis using Hubble and STIS and the X-ray analysis using the 0th order HETG spectrum. So one thing that is important to note is that first, if the iron 10 and the X-ray gas had different distribution, we would not be able to see this agreement here. And in thinking about it, there is no reason a priori to assume they would have the same distribution, except for the fact that they peak over the same range in ionization parameter. So this here is a very important and very exciting result, because this means that our method really works, which means that we don't need to have very accurate X-ray kinematic data to measure the physical properties of these X-ray winds. We can take advantage of the amazing spatial and spectral resolution of Hubble, for example. And this also allows us to quantify these outflows for more distant galaxies, for which is almost impossible to obtain any good X-ray kinematic information. And we still need X-ray observations to constrain the physical characteristics of this gas for our photoionization model analysis. But the fact that we can use the kinematic information for the footprint lines is what makes this method so important. So in this case here, we use iron 10 to track these X-ray outflows because of the characteristics of this AGN. So NGC 4151 is a weak AGN. So for AGNs with more highly ionized gas in their narrow line region, other lines would be a better choice, such as silicon 10, for example. And this is another reason why it's important and necessary to know the characteristics of this X-ray gas, because we need to be able to know which footprint line would be the best tracer, let's say, for different agents. So this, we'll probably submit this study to the journal next week, and I'll be happy to answer any questions that you have regarding this analysis or our studies on X-ray outflows, or even my studies on optical outflows. So thank you very much.
Thanks very much, Anna, for a great talk. Do we have any questions? As usual, please feel free to put them in the chat or raise your hands. Don't be shy. Yes, we have one question in the chat. Could you mention again how the footprint lines differ from the coronal lines?
Oh, okay. So let me just go back to this. So for instance, we have here iron 7, which is this blue line here, which is a coronal line. So the footprint lines are a subset of the coronal lines. And we consider a footprint line lines that have ionization potential that is greater than the 0.7 ionization potential. And as we can see here, I really like this plot because you can really see the difference. So the iron 7 is a coronal line, but not a footprint line. And this is also shown here because you can see that it peaks at a much lower ionization parameter when compared to this to the O3 to the footprint lines. And the thing that I mentioned actually, the end of my talk, for quasars or for AGNs that have a more highly ionized gas in their narrowline region, a good tracer would be, for example, silicon-10, as we can see here, because it peaks at a higher ionization parameter. So yeah, so basically how we define footprint lines is they are coronal lines that have a ionization potential that are greater than that of the O7.
Thank you. And thank you for the question, M. Ravalsky. I'm not entirely sure who that is, but thank you. Next question is from Dan Schwartz. How did you deproject the velocities?
So the velocities were deprojected. Where is it? Here. I didn't have time to talk about that because it's a very short presentation, but the way Fisher et al. 2018 deprojected these velocities and the way we also did for my paper on optical outflows, we used a Bayesian routine. We fit the emission lines with Gaussians, and then we can calculate, we can get measurements like the velocities and the width F maximum. And just a matter of curiosity, this image here is a optical ground-based image of these galaxies, and this is the image that we use to deproject our distances.
Cool, thank you. Any other questions? All right. Looks like we don't have any other questions for the moment. So both speakers have openings on their meeting schedules. So if anybody would like to speak to them, please go ahead and sign up. And thank you again to our speakers. Thanks for joining us. Thank you all for joining us, and have a wonderful rest of your week. We will see you next week.
Thank you.
Thanks, everybody.